Good morning to all. I am Dr.N.PRABHA, Assistant Professor of Chemistry, A.D.M. College for Women, NAGAPATTINam. Today I am going to discuss about thermodynamics. This unit belongs in Physical Chemistry 1 for 3rd BSc Chemistry, Module 1. In this module, I want to discuss about why we need for the second law of thermodynamics, what are the different statements of second law of thermodynamics, Carnot cycle and Carnot theorem. First, let us see why we need for the second law of thermodynamics. In the first law of thermodynamics states that energy is neither created nor destroyed, but energy change from the one form to the another form. Delta E is equal to Q minus W. In the first law, gives the definite relation between the heat absorbed Q and work done W by a system in a given process, but it does not give the direction of flow of heat. That is, we know from the experience that transfer of heat from the lower temperature to the higher temperature is not possible without spending energy. But according to the first law, both transfers are possible, which is not correct. This means first law is unable to give the direction of the flow of heat. In the second one, according to the first law, the energy of an isolated system remains constant during a particular changes of system state, but it is unable to predict the feasibility of a reaction. That is, it is unable to tell whether a change of state or a reaction can take place spontaneously. For example, if you take the metal rod of uniform temperature, cannot become cooler at one end and hotter to the another on its own accord. That is, this process is not feasible. But according to the first law, this process is impossible. It only stipulates the conditions that this process takes place, then the heat lost at one end will equal to the heat gained at the another end. And the third one, according to the first law, one form of energy can be converted into another, but it does not indicate the fact that heat energy cannot be converted into work. Because the limitation of first law, we need another law to predict the direction of flow of heat, to predict the feasibility of the reaction, and to find out the fraction of heat absorbed that could be converted into work. That is why we need the second law of thermodynamics, which gives answer to all the above mentioned points. From the second law of thermodynamics, we define a new term, that thermodynamic property called entropy. Also, we define some related properties, studying the changes of these properties in a system. We propose certain conditions for reversible and irreversible process. This condition are used to predict the feasibility of a chemical reaction. Now let us see different statements of second law of thermodynamics. First one is the Clausius statement. In Clausius states that it is impossible to construct a device operating in a cycle that can transfer heat from a colder body to a warmer one without consuming any work. That means heat cannot be transferred from a body with the lower temperature to another with the higher temperature by a machine by itself with the help of some external agency. In the second statement, Kelvin statement, it is impossible to construct a machine working in cycles which can convert heat completely into an equivalent amount of work without producing changes elsewhere. That means a machine working in cycle converts heat into work only partially. A ratio between work done and heat absorbed, W by Q, is always less than 1. Third one, all other forms of energy can be completely converted into heat, whereas complete conversion of heat into any other form of energy is not possible. That is, conversion of any form of energy, namely electrical, chemical, mechanical, that etc. Heat is not possible. But heat cannot be completely conversion into any other form of energy. Fourth one, all spontaneous processes are irreversible. That means all natural processes are irreversible. For example, water flows down from hill spontaneously. If cannot climb up the hill spontaneously, that is the non-spontaneous process. In the second example, heat flow from the hot end of the body to the cold end, but the reverse does not happen on its own accord. One, in a reversible process, the entropy change, delta S of the system and the surroundings taken together remains constant. In an irreversible, it increases, delta S greater than 0. That means entropy of the universe, which is measure of unavailable energy, and the randomness is increasing. Sixth one, in a reversible process, free energy change, delta G of the system and the surroundings taken together remains constant. In irreversible process, delta G is decreases, that is delta G less than 0. That means free energy of the universe, which is measure of available energy for work, is decreasing. Now let us see some fundamental terms. What is meant by heat engine? The heat engine means flow of heat from the hotter body to the colder body is a spontaneous process. The heat that flows out spontaneously can be used to do work with the help of suitable device. A machine which can work by using heat that flows out spontaneously from a higher temperature, that is the source, to the lower temperature, that is zinc, is called heat engine. The steam heat engine is a typical heat engine, is an example for the typical heat engine. It takes heat from the boiler and converts some heat into the work and returns the unused heat to the surroundings. Boiler is the source and the surroundings are the zinc. Now let us see the Carnot cycle. In Carnot cycle, there is the Carnot engine. The Carnot engine is a theoretical thermodynamic cycle proposed by Leonard Syed Carnot. It estimates the maximum possible efficiency that the heat engine during the conversion process of heat into work, and conversely working between two reservoirs can possess. The Carnot cycle was first developed in the year 1824 by the French physicist. It is an ideal cycle that basically laid the foundation for the second law of thermodynamics. The Carnot cycle also brought up the concept of reversibility. In a Carnot cycle, a single cycle of Carnot engine is referred to as a Carnot cycle. In a single Carnot cycle, there are the four processes. It involving in the four processes. First one is stage 1, reversible isothermal expansion. Stage 2, reversible adiabatic expansion. Stage 3, reversible isothermal compression. Stage 4, reversible adiabatic compression. Let us see each steps as follows. In a first step, reversible isothermal expansion. The cylinder is placed on the source so that the gas acquires the temperature T2 of the source. It is then allowed to undergo expansion. As the gas expands, the temperature tends to fall. Heat passes into the cylinder through the perfectly conducting base, which is in contact with the source. The gas therefore undergoes slow isothermal expansion at the constant temperature T2. Let the working substance during isothermal expansion goes from its initial state A to final state B. That the pressure changes from P1 to P2, volume changes from V1 to V2, but throughout the process temperature is constant T2. That is, you know the first law of thermodynamics, delta E is equal to Q minus W. In isothermal expansion, delta E is equal to 0. So, that is Q is equal to W. W1 is equal to RT2 ln V2 by V1. For in first reversible isothermal expansion, first work done W1 is equal to RT2 ln V2 by V1. In the second stage, reversible adiabatic expansion. Adiabatic means heat change is constant. In the second stage, the ideal gas is at temperature T2 is allowed to expand adiabatically. The volume changes from V2 to V3 and the temperature T2 reduces to T1. So, heat change is equal to 0. That means Q is equal to 0. So, work done W2 is equal to CV delta T. CV W2 is equal to CV into T2 minus T1. In the stage 3, that is reversible isothermal compression, the gas is placed in the reservoir at the temperature T1, is in compressed isothermally and reversible such that its gas heat is Q1 to the reservoir. Thereby the volume decreases from V3 to V4. That is, heat change is equal to minus Q1. Work done W3. W3 is equal to RT1 ln V4 by V3. That is, W3 is equal to minus Q1. In the stage 4, that is reversible adiabatic compression. That is the final stage. The gas is compressed adiabatically and the temperature increases from T1 to T2. The volume reduces from V4 to V1. Thus, one cycle is completed and the gas returned back to the initial state during the fourth stage. Heat change is equal to 0. W4 is equal to minus CV into T2 minus T1. Now, the sum of the total work done in the cycle in the 4 stages, W is equal to W1 plus W2 plus W3 plus W4. Substitute all the values. W is equal to RT2 ln V2 by V1 plus CV T2 minus T1 plus RT1 ln V4 by V3 minus CV into T2 minus T1. In the reversible isothermal expansion and reversible adiabatic expansion and adiabatic compression values are cancelled because plus CV T2 minus T1 and minus CV T2 minus T1 is cancelled. So, W is equal to RT2 ln V2 by V1 plus RT1 ln V4 by V3. The heat absorbed from the reservoir at T2, Q2 is equal to RT2 ln V2 by V1. Now, you calculate the efficiency of the heat engine is equal to W by Q2. Substitute the W value and the Q2 value. W by Q2 is equal to RT2 ln V3 by V2 by V1 plus RT1 ln V4 by V3 divided by RT2 ln V2 by V1. You have already known adiabatic expansion of the system T V power gamma minus 1 is equal to constant. So, you simplify the values and finally we get V4 by V3 is equal to V2 by V1. Substituting these values in W by Q2, that is RT2 ln V2 by V1 plus RT1 ln V1 by V2 divided by RT2 ln V2 by V1. That is, you can take the same values, or W by Q2 is equal to T2 minus T1 divided by T2, R ln V2 by V1 divided by R ln V2 by V1. Both the terms are cancelled. W by Q2 is equal to T2 minus T1 divided by T2. That is the efficiency of Carnot engine, eta is equal to W by Q2. That is equal to T2 minus T1 divided by T2. That is giving in the working temperatures. Any other heat engine working reversibly between these temperatures will have the same efficiency. This efficiency does not depending upon the working substance design of the engine, because as per the above equation, efficiency depends on only the temperature of the source and zinc and nothing else. Eta is equal to T2 minus T1 divided by T2. Suppose, that is, you can simplify the equation, eta is equal to 1 minus T1 by T2. That is always less than 1, because T1 is equal to 0. If you take T1 is equal to 0, then eta is equal to T2 by T2 is equal to 1. That means we use the zinc in the Carnot cycle. Those temperature is absolute 0, then efficiency will be 1. But 0 Kelvin is unattainable. So, eta will always be less than 1. The heat engine cannot work between two reservoirs with the same temperature, because T1 and T2, T1 is equal to T2, then efficiency is 0. This means the machine cannot work. Now, let us see the Carnot's theorem. This Carnot's theorem is from the second law of thermodynamics. Two important results are derived, where the conclusions are taken together to constitute the Carnot's theorem. It states that no engine can be more efficient than a perfectly reversible engine working between the same two temperatures. The next statement, the efficiency of all reversible engines working between the same two temperatures is the same, whatever the working substance. Now let us see the explanation. First one, to prove the first part of the theorem, we consider the engines R and I working between the temperature T1 and T2. T1 is greater than T2. If of the two engines, R is reversible, I is irreversible. Suppose I is more efficient than R. In each cycle, R absorbs the quantity of heat Q1 from the source at T1 and rejects the quantity of heat Q2 to the zinc at T2. Similarly, in each cycle, I absorbs the quantity of heat Q1 from the source at T1 and gives the quantity to the heat Q2 at the zinc to the T2. Let the two engines do the same amount of work in each cycle. According to the assumption, I is more efficient than R. Therefore, Q1 dash minus Q2 dash divided by Q1 is equal to Q1 minus Q2 divided by Q1. W by Q1 dash greater than W by Q1. So, that is Q1 greater than Q1 dash. So, therefore, Q2 greater than Q2 dash. Now, if the two engines are coupled together so that I drives R backwards, and suppose they use the same source and zinc, the combination form a self-acting machine in which I supplies external work W and R absorbs this amount of work in the reverse cycle. I init the cycle, absorbs heat Q from the source and gives heat Q2 to the zinc. In R in the reverse cycle, absorbs heat Q2 from the zinc and gives heat Q1 to the source. The net result of the complete cycle of the coupled engine is given by T1 is equal to Q1 minus Q1 dash, and the heat by the zinc T2 is equal to Q2 minus Q2 dash. External work done W of the system W is equal to 0. So, the coupled engines forming a self-acting machine unaided by any external agency transfer heat continuously from a body at a low temperature to the body at a higher temperature. This conclusion is contrary to the second law of thermodynamics, according to which in a cyclic process, heat cannot be transferred from one body to the another at a higher temperature by a self-acting machine. Hence, our assumption is incorrect, but we conclude that no engine can be more efficient than perfect reversible engine working between the same temperature. In the second part of the Carnot theorem may be proved by the same argument as before. For this purpose, we consider two reversible engine R1 and R2. Assume the R2 is more efficient than R1. Proceedings in the same way, we can show that R2 cannot be more efficient than R1. Therefore, all reversible engines working between the same two temperatures have the same efficiency. Thus, the efficiency of a perfectly reversible engine depends only on the temperatures between the engine work and is independent of the nature of the working substance. Thank you.